Okay, this is multiple choice one. Go and get started with question one. Most important thing about these, first of all, identify what kind of question. I'm seeing numbers in the question. I see numbers in the answer. When you see that, you're probably going to want to write letters like symbols instead of drawing a picture. Not always, but on these, they're a little bit easier sometimes. This one has a pretty interesting trick. Let me show you. Okay, so I would start off car. Okay, so I've got a car and it has a tire. Now look, be real careful here. Look for S's or like plural. I'm seeing a car that has a tire. So I'm thinking object that has a rotational inertia right there. Rotational inertia, that's like rotational mass. I'm going to put I. Okay, and then I'm going to underline the number. I can go back and look at that. The instant. Words like instant, instantaneous, and average, things like that, look for. Instant, so it's just like split second. The tire has a counterclockwise. Okay, so that would be positive. Remember, counterclockwise positive because of that thing. Okay, so counterclockwise. Anyway, as a counterclockwise angular velocity, that's omega with the arrow of, 6 rads per second. And average, look for words like average too. So we've got instant and average. Counterclockwise, that's positive again. Torque, Miley with Rihanna's umbrella, 5 Newton meters. So I'm going to put torque, and you can write average down there, but remember you can also do that bar on top that means average. Average torque of 5 Newton meters is applied for 4 seconds. So that means it's like 0 seconds, 1 second, 2 seconds. So this is time. Or if you think about it, since it's kind of giving you like a time range, it could be change in time. Either or. Although change in time is more specific. What is the tire's change in angular momentum? Now this, they don't underline stuff. I mean, if they're underlining it, there's a really good reason. So that's important to note. And then in angular momentum, remember it's the angle that looks like the L, arrow. That's angular momentum. Okay, and they want change in angular momentum. So that's delta L, or delta angle L thing. Okay, so this change in angular momentum is the thing that you were looking for. I am going to put a star by it. Maybe circle it. I don't know. This is the thing I need right here. So anyway, what is that? Well, I'm sure you all have this in your head because, you know, I said to do it so many times. But look, it's the bridge equation sheet. So useful. All right, so delta angular angular momentum. Hey, that's just like regular momentum over here. And there are, it looks like that is rotational inertia times omega. But that's not quite the same thing. That's kind of how they want to trick you here, because this is the equation. It's on the equation sheet and everything. But this says two very important things. One, it says change in. That's like change in momentum, which is like impulse, and like regular impulse, and then the average. So the way I would think about this one is I would know that the change in regular momentum is average force, like when we drop the cars on the force sensor, average force delta time. So the rotational version of this would be, change in angular momentum would be, rotational force is torque, it's average, didn't put the little vector. Change in, what's rotational time? Just kidding, it's just time. No such thing that we know of. So yeah, it looks like since I have the change in, I would need my numbers for torque and my numbers for time. And they know you're going to want to get in here and like plug in the first two numbers you see. But the keys here are change and instant. And then the average also kind of tips you off. But instant, that's just like a split second. It's not like a change in. So anyway, your numbers would be 5 Newton meters. Remember, torque, that's not a joule, that's just a Newton meter, times 4 seconds. So that would be 20. Answer is C. Okay, so 2 is pretty easy. This is one you'd use your ruler for. A wooden plank is resting on a flat, frictionless surface. If the tablecloth is like plastic and too rough, I think they're going to put paper though, just, do this on the test booklet. It can rotate freely about a vertical axis on the rightmost end. See this? This is its pivot right here. Below are figures depicting forces of different magnitudes exerted at different places on the plank. Okay, so force and how far it is would be R. What is that? Oh no, it's Miley. Yeah, anytime you have a force and a radius, remember Miley needs more force than Kim Kardashian, not so much radius. You have Miley, and the symbol is Rihanna's umbrella. So it's radius cross product, which means sine theta, which you probably won't use, radius times force. That's how you get your torque. Okay, so, but I mean, yeah, and it wants to know which one increases the plank's angular speed about its axis fastest. I mean, change in speed or change in velocity, that's acceleration. So basically, which one makes this thing move fastest? The equation might help you, but acting it out is going to be better. So yeah, set your ruler up like this, and if you want to get really specific, you can just use different size pencils, or you can just hit it harder or softer in different places. So let's look at the first one. That'd be just like, oops, one pencil right here. So if you hit this like really hard right here, it'd probably go flying pretty fast. That is not rotating where I wanted it to, but you get the idea. It'd probably rotate pretty fast if I hit it right here. So A is a possibility. So I'll put like, squiggly, maybe. Okay, now let's look at B. It's like twice the force, so that would be, move these guys. So twice the force at B. Just make the pencil longer. Anyway, yeah, that's still probably go pretty far. But, and we're guessing, oh, you know what? That doesn't look like that's quite, I think that's like over here a little bit. So maybe B, but I think A is a better answer. So I'm going to still stick with A. All right, then 2 half forces at the same time, one at the end and one right here. Yeah, that's still not going to be as good because if you like multiplied half times like half the ruler and whole, yeah, that one doesn't seem like it would go as far. And then if you had like down here, and I think some of you maybe just didn't see this drawing, if you had like a force here and a force at little force at the end or something like that, that doesn't seem, yeah, you got a bigger force pushing it down. I think that one's going to go backwards. So A is the best answer, I think, here. But this one really, ones like this that have pictures, you can usually just do by acting them out. That's what the ruler's for, because you're not going to need to measure anything. Okay, this is one where I would probably get up and go to the bathroom and like lean up against the wall if I couldn't figure it out. Let me show you, or if you can imagine that. So this says a ladder rests against a sturdy wall at an angle. Which of the forces below is equal to in magnitude to the force of friction exerted on the ladder by the floor? They usually say magnitude, but in this one I think kind of the direction might matter a little bit just for figuring it out. So anyway, this would be like the ladder situation. That's interesting, but let me show you what's more useful. It's better if you pretend to be the ladder. So if you lean up against the wall like this, and what I would do, picture doing this. Now think about what forces act on you. Think about your feet and your socks and which way those slide. That would be kind of the first thing you notice, or if you had on flip-flops or something. the way that your socks would slide and your shoes would be your force of friction. So, I mean, you can get up and try this. It's kind of interesting to see. So your force of friction would go that way. Now, you know that this isn't rotating. Like if I removed this wall, this guy would just fall over. But he's not. So something has to balance out the force of friction. And if we looked at like, I don't know, center of mass somewhere around in here, if he were to rotate about the axis, like if there were no wall, it'd just be like falling over. So anyway, there has to be a force going this way, like this way, to balance him out. So if you look at that, if you think about how it feels, see how his back squished? There's a force from the wall pushing on this guy, or you, or the ladder, going that way. And that is 90, his back is 90 degrees to the surface. So that would be the normal force of the wall. Yeah, this is just one that's good to act out, either act out in your mind, or if you have to get up and go act it out, that's fine too. So let's look. The gravitational force of the ladder. Nope, not that one. The normal force from the wall on the ladder. Probably that one. Let's just double check. The force of friction from the wall on the ladder. No, because that would be force of friction would be pushing your shirt up or down. It works the other way. Okay, the normal force of the floor on the ladder. No, because that would be going up this way. Again, the wrong direction. So yeah, it's B. Okay, this is one of the lab multiple choice ones, and always think about how you would do this in class. If I'm like, oh my God, you have like 10 seconds to get stuff out of the junk pile. How are you going to test this? What are you going to need? What do you need to measure? Just think about that. All right, so this says, it's supposed to say a disk, sorry, of known rotational inertia. So let's kind of just put that. That's like the rotational mass, and a known radius. I might just actually draw this. You never know, sometimes it's good to draw them. I'm not drawing with the mouse. Anyway, it has a known radius, can rotate freely without friction, that's important, around a central fixed axis. So that would be like its fixed axis right there. A disk has a string of negligible mass wrapped around its edge. Okay, so it's like a yo-yo. So here's the string, which may be pulled, causing the disk, which was initially at rest, always important, the disk is not moving at first, to rotate. Okay, so this is a string, so it would do this, so that'd be like the force of tension. And then its initial angular velocity, because it's at rest, is 0. And then it will start to rotate. So once you pull. Okay, what would be the best procedure to determine the relationship between the applied torque? So if you look at it, applied torque, so probably the force of tension, that's going to be the thing you change, like your input, and the change in angular momentum. Change is important. So change in angular momentum would be delta omega. Wait a second. This looks like one I saw a minute ago. Hey, look at this. Change in angular momentum and torque, and then you have time. That seems useful. I'm glad they asked that question. Be careful. Sometimes they'll ask ones that aren't like that, but sometimes you can get information that way. Just read things carefully. So I'm going to say this has to do with torque, change in time, probably average torque. So let's look and see, this might be important. And are there ways to measure this? I can measure the radius with a meter stick. I can measure, so like meter stick here. Here I could have a spring scale. I'm just drawing pictures. You don't have to label stuff on your multiple choice. That's a spring scale. Okay, and I just labeled it for y'all. And then time stopwatch. That's a stopwatch. Anyway, so let's look and see. They usually want to know like lab procedures or like how to measure stuff. So let's look and see. So, okay, so it says A is exerting a force of 45 newtons on the string for 6 seconds. So we would have, okay, we know the torque, we know the time, and then for 75, so we could maybe figure this out. Okay, so, but which one are we varying? We should probably be varying torque. Okay, so we are, because if you change the force, you would be varying the torque. But then we're also varying the time. So it can't be that. You don't want to vary, you don't want to change two variables, so it can't be A. Okay, exerting a force of 45 newtons, changing the torque, that's good, because when you change the force, you change the torque, on the string for 4 different times intervals and measuring the angle through which, okay, so right here, you're changing the time, and that's not what it asked. It said the relationship between the applied torque, so it cannot be B. Okay, exerting a force of 45 newtons on the string for 4 different times. Well, no, that doesn't work either. We are not changing the time. This one says exerting 4 different forces. Okay, it has to be this one, and yeah, that's what I needed to see. So that's D. That's the answer.